Okay, in the last class, we started to look at the frequency response on the pole zero locations for a common source amplifier, and in particular in the presence of a source resistance. Right, so this was the circuit. We had the input source, the source resistance, and we had capacitance at the input C1, the transistor, and at the output side we also had R0 C0, and we call this capacitor to be C, right? And I mean later I just replaced this transistor by a GM block for the sake of convenience. So basically this was replaced like this, right? Let me draw it. So how many poles and zeros does it have? 2 poles and 1 zero. So we intuitively found out the location of the zero, and but with respect to the poles it is not straightforward because of this coupling between these two nodes. So we kind of calculated the exact transfer function. So we got a quadratic equation, and what assumption did we make to simplify that equation further? To get the pole locations, what was the assumption we made to solve the quadratic? That one of the poles was basically smaller than, or the other pole is greater than the, that is one of the poles is much greater than the other pole. With that we got some approximate expressions for the poles, and we were in the process of making sense of those expressions. And let me first copy paste that first pole expression maybe. Yeah, I think this guy. So this was the big expression we got, and we saw this makes sense because at the input side, if you notice, this capacitor is connected between these two nodes, and at low frequencies, what is the gain from this node to this node? Minus Gm by G0. So we basically use the Miller approximation, right, to reflect this capacitor which is connected between two nodes into a single capacitor at the input side. And if I do that at the input side, I'll have the resistor Rs. I'll not show the input source because it's not relevant to us for pole calculation. We have the capacitor C1, and the capacitor C, how does it come here? C into no, so 1 plus. I mean, if you had a, I mean, the Miller effect was this. Please remember, we had a voltage amplifier with a gain minus A. If we had a capacitance C connected across this, the idea was if this voltage was some V test, this is minus A times V test. So voltage across the capacitor is what in this polarity? Basically 1 plus A times V test times C. So it looks like at the input you have a capacitor. I mean, this I can replace it. Just to model the input side, I can say that I have a capacitor which is C into 1 plus A, right? So what is the capacitance I should have here then? 1 plus Gm by G0, okay? And then you have the trans connector and something. So now the input side is kind of decoupled, so you can say what is the pole location at this node. So this gives the approximate expression as the conductance is Gs and the capacitance we have C1 and the Miller multiplied capacitance, just this, right? and we see that we have GS here. We have C into 1 plus Gm by G naught. We also have C1, right? We do have additional terms like this, and this is basically because this itself is approximate expression. And also, as I mentioned in the last class, Miller effect can be applied only when you have a voltage controlled voltage source like this, right? The voltage controlled voltage source fixes the relation between these two node voltages irrespective of what's happening in the rest of the world, right? But whereas here we have a voltage controlled current source, so this doesn't fix the voltage relation between these two nodes, right? It just fixes what this current is, and the voltage in turn depends on what you have here, right? So you can't actually apply Miller effect, it is just an approximation. So that is why we have all these error terms. But for all practical purposes, what you will find is the terms which I have highlighted in yellow here, they will only dominate, because you see this capacitor is getting multiplied by some gain. If you assume all capacitances are of the same order, the capacitance that is multiplied by the gain is what is going to dominate. So you can always approximate like this, right? Although this is not very accurate, for all practical reasons this is actually a good enough approximation for us to work with. Okay. Great. So now let's try to make sense of the second pole location. So what I'll do, I'll copy paste the second pole location once. This is the second pole. Okay, yeah. This was the second pole location we got. So let me draw the circuit once again. We had at the input I had RS, C1, I had this GM block, C, R0 and C0, right? So now let's look at the output side. At the output side, if you think about it, if I try to draw only the capacitances I have C0, right? I have this capacitor C, and I also have C1. If I just draw the capacitances alone, this is what I have, right? And this is the output node we are interested in. Sorry, this color changed here. So this is the output node. So at the output node, what is the effective capacitance you have now from here to ground? C0 plus series combination of these two, right? So that is basically what you have here, isn't it? So what you have here is basically C0, which is in parallel with C and C1 in series. Okay. So now the denominator term makes sense. So now let's look at the conductances we have. So of course at the top we have conductance G0, that is 1 by R0. So that is taken care of here. But we also see we have a term involving Gm, and this makes sense because if I were to draw the Gm here, we have something like this, right? So the conductance is basically what? If to find the effective conductance, I can apply a test voltage source, and I'll find what is the real current that is being drawn, right? Imaginary current is from the capacitor, only the real current is drawn by the conductance. So this guy will draw a real current of V test by G0 that we already included. So now if this voltage is V test, what can you say about this voltage? This is V test. You have some structure like this, and here this doesn't take any current. It's basically a voltage division between the capacitors. So what is that voltage? Okay. So this is the voltage you will have at the input of the transconductance. So what is the current that it sinks? I mean, look at the direction I have drawn. I have. What is the current in this direction? I mean, you know, this voltage is 0. This voltage is whatever you have told. Huh? GM into that voltage. Is that okay?
Yes.
So this current is GM times C by C plus C1 times V test. Okay. So that basically is this term. Okay. Now, of course, you also have a term involving GS. That's basically because you also have an RS here. So you have some additional terms. But the point is again, sorry, this guy, this comes because of this. But the point is again, if you think about it, in the numerator, which of the terms do you think will dominate here? Which term do you think will be the dominant term? It's going to be GM, right? Because GM is going to be much higher than all the other conductances. Okay. So finally you will see that this term is the guy which will dominate the numerator. Okay, because GM is going to be greater than G0 and all the other conductances you have. So again, for all practical reasons, you can still approximate this as G0 plus GMC by C plus C1. Of course, this in turn can be approximated as this term alone. By you have C0 plus okay. So now we have I mean, now at least it makes sense why the pole locations come out to be like this, right? So to summarize, let me take this circuit once again. Okay, fine. Yeah, so let us say now here I don't have the capacitance C. That is, this capacitor is not there. So do you think the nodes here are uncoupled or they are coupled? They are uncoupled. So can you comment on the pole we'll have at the input side?
GS by C1.
That's minus GS by C1. Okay, it's not even approximate, this is exactly equal to actually. And what about the pole that will arise due to this capacitor? Minus G0 by C0, right? Because that side is completely uncoupled. So now the moment we added C, what is the first pole here? We just saw it, right? So we'll have the conductance is minus GS. The capacitance is going to be the existing capacitance C1 plus this guy multiplied by the DC gain of the amplifier we have, which is C times G0. Okay. Now similarly, the second pole we'll write at the capacitance we saw we have C0 in parallel with these two fellows. So you have C0 plus C1 by C plus C1, and with respect to the conductance we have this G0 plus you also have a capacitive division between C and C1 that is contributing, I mean, and that factor times the GM will also sink in some real current. So that conductance is what? GM times C by C plus C. Okay, great. So this is now two cases. So this is before C, this is after adding C. So now can you tell me here if this pole has moved to a lower frequency or a higher frequency? Huh?
If you consider the negative sign,
No, okay, forget about the negative sign. I mean magnitude. I mean
lower.
it has moved to a lower frequency. What about this guy?
Cannot say.
Good answer. It cannot say because you see that both numerator and denominator have increased. I mean, but let's find out which of the increase is more dominant, right? So if you think about the capacitances, let's say all of them are roughly same. So capacitance increases by around 50%, right? Roughly. But the numerator we have along with G0, we have this guy. And I know GM is going to be much higher than G0, right? So now can you comment on whether this pole has increased or decreased? It has moved to a higher frequency. Okay, let me include the minus sign here. Okay, right? So now again earlier these two guys, again if all conductances and capacitances were of the similar order, they might have been close by. Okay, but the moment you add the capacitor, one of the poles has shifted to a low frequency, the other pole has gone to a higher frequency. Okay, and this act is usually called pole splitting. So we'll return to this in a few classes down the line. Okay. And again, remember when we tried to solve the quadratic equation here, we made an important assumption, and what was that? So we assumed that one of the poles is much greater than the other, right? Now we have solved it. If you are a good engineer, you make sure that the assumption is valid. So do you think the assumption is now valid here? It is valid, right? Because again, as we saw earlier, the poles were close by. But the moment you added the C here, one of the poles has moved to a low frequency and the other is at a higher frequency. So obviously one pole is actually greater than the other. So this is satisfied. I mean, this is a crucial part of any solution you do. It's okay to make any assumption, but you should make sure that that assumption is valid at the end. Great. Oops, this is satisfied. Okay. Great. So now we have seen the common source. So next, what is the next amplifier we should look at? We saw common drain. Common gate is an exercise for you. What is the next amplifier we looked at? The differential amplifier, right? So we'll straight away go to the main guy, the 5 transistor diff amp. Okay, so this is V1, V2, this is V out. So again we can start to mark the capacitances one by one. Now obviously from each of the nodes to ground you will have a capacitance, right? And that will be due to whatever, source to bulk, drain to bulk, whatever. And we will also have capacitance, the CGD capacitances everywhere, right? But of course now you see you add capacitances at each of the nodes, things actually become quite complicated. So what we'll do is we'll make some assumptions. So let me erase this. So first assumption we'll make is that, okay, we'll make some approximation. The first assumption is that the capacitances CGD are negligible. And in practice it's actually a very reasonable approximation, because if you remember from the MOS device construction, What is the gate to drain capacitance? Why does it come about? It is basically the overlap capacitances, and that's actually pretty small compared to the oxide capacitances we have. So this is actually a very reasonable approximation in practice. Okay. Even in the earlier examples we could have done that, but if I neglected it, there might not have been any capacitance. So that's why I didn't neglect. But here we can do it. So which means we'll only have capacitances from each of the nodes to ground. That's all. Okay. So here I'll have a capacitance. So I'll call it CL. I'll club it with the load capacitance. So I'll have one more capacitance here. And one more capacitance here. Okay. So I'll call it C1 and C2. Is that fine? So next, we know that if you have an RC like this, C1 and R2, C2, what are the pole locations here?
C1 by C1.
Yeah, minus what? You can say it because the two nodes are uncoupled, right? So let's see if we have something similar here. So do you think now these two capacitors are uncoupled or they are strongly coupled? Is there any direct connection between these two fellows? No, right? I mean, you might have had if you actually had considered CGD,
Yes.
but we safely ignored it. So these two are not coupled. So what about these two? Or for that, I mean, or that factor, I mean, for that matter of fact, C1 and C2? Is there something that directly connects? What is it?
Drain to.
Huh? In the incremental equivalent, finally, if you in the small signal picture, is there?
Current source.
No, okay. See, current source is fine because see, basically you are saying this current source, right? This is an ideal current source. I can say that the current source is also coming from anywhere to anywhere. This can even be floating. This will still pump in a current. I mean, the point is when I mean coupling, you will have something like this, which means you will have current flowing from one node to the other. Right? The current source is not pumping in a current from this node to this node, right? So is there something else that can introduce coupling? The R0, right? So we'll have an R0 here. So that will make sure current can flow between these two guys. So this will introduce coupling. So we don't like coupling. So what can we do? We are in the process of making assumptions. So, you'll assume that R0 for the NMOS is infinity, or it's very very large. Okay. I mean, again, see here when we had a buffer, we could isolate and say the pole locations, right? But it turns out even if you don't have the buffer, if one of the time constants is much greater than the other, the pole locations are still these. Okay. And logically it should make sense because when you had a buffer, it made sure that the looking in input impedance is very large. I can as well ensure this condition by saying that this R2 is a much large resistance. Okay. So in our case also we'll assume that the NMOS has a large output resistance, or actually we'll say it's infinity here. Okay. Great. So if you make the assumptions, now things get simplified. So let me redraw the circuit again. So we have this guy. I'll draw only the incremental equivalent. So here I'll have only the capacitance C2. I'll have the two PMOSes. This is ground. Okay. I'll have C1 here and CL. This is incrementally ground. Great. So let me push it to some side here. So this is V1 and V2, and I've assumed that R naught of the NMOS is infinity. So can you say about anything about this guy Vx? When is it average of the two? Huh? Sorry? Yeah, I mean, okay, in fact, this was one of the problems for you to work out. So, yeah, one condition, it turns out that this is infinity, but there is also some other thing that actually needs to be satisfied. Okay, so let's quickly check it, right? So, let's say incrementally I have only these two current sources, R naught is infinity. So, at this node, if I apply KCL, what do I get? Gm of NMOS times, what is the value of this current source? V1 minus Vx plus the other current source, which is equal to Y0. We have a path here, right? Vx into SC2. Okay. So, I mean, so if I want V1 plus V2 by 2. That's what everyone wants. What is this equal to here? Ideally, you'll have something plus something. What is this? Simple algebra, right? I mean, I want here I want V1 by 2. So what I should divide this by? By 2 times Gm. I have to divide the entire thing by 2 Gmn, so that this becomes V1 by 2, V2 by 2. So here I'll have 2 times Gm times Vx, so that becomes Vx plus Vx times SC2 by 2 Gmn. Okay, it's the manipulation. So what is the condition to ensure Vx is V1 plus V2 by 2? I mean, Gm tending to infinity is fine. I mean, that you cannot ensure. What is the other simpler condition you can have? No, Gm we can't say, right? Gm is, only thing is, only if C2 is 0, that is true. So in other words, any impedance here connected to this common source node, which is also called the tail node, that should be infinity. Okay. So in case I have not introduced the term, that node is called tail node. If these two are satisfied, you can actually say this. Okay. And this node, let me write it here. This is called the tail node. Okay, so this is fine. So now what I'll assume is, I'll assume that V1 is plus delta V by 2 and V2 is minus delta V by 2, because we are interested in only the differential response. The common mode response, I'll give it as an exercise. So if this is the case, what is Vx? 0. From here it's straightforward, it's 0. Okay. Again, this should not be surprising, because I have assumed that R0 for the NMOS transistors are infinity. So what can you say about looking in impedance here into the source of the NMOS? It's 1 by Gm. Similarly, here it is 1 by Gm. See, ideally it depends on what is the resistance you have at the drain. But if R0 is infinity, it is 1 by Gm, right? As long as the resistances here are finite, if R0 is infinity, this is 1 by Gm, right? So from this node it looks like it is two identical resistances. So at this node it looks like everything is symmetric, right? So which means if I increase this and decrease this by the same amount, all the nodes at the line of symmetry they will be at 0. That we had already seen, and that's what happens here. So if Vx is 0, do you think C2 is relevant or not relevant? I don't have to worry about it, right? So C2 plays no role here. Okay. So let me redraw the circuit cleanly. So now the point is, if V1 and V2 are chosen to be a differential input, this guy will be incrementally short.
But sir, we cannot comment on C2.
We are not saying anything about C2, right? C2 is still there.
We assume Vx equals to V1 plus V2 by 2.
No. This is with C2, this is the expression, right? So even here, if I assume this condition, this guy will be 0. Is that fine? This condition is Vx is 0 if you choose this fellow, irrespective of whether you have C2 or not. That fine? In the presence of C2, this was the exact expression we got. And here I put the inputs to be this, Vx comes out to be 0. So this, the only assumptions that need to be valid are not as infinity for this. So, okay, or the other way around. Okay, so which means now this is virtual short. That should simplify the circuit. So let me draw that properly. I have this guy, and this is virtual short. So to explicitly show it's at ground, I'll just mark it like this. At the top side, I have the PMOS current mirror. Okay, so this is also incrementally short. I have CL and C1. So this is plus delta V by 2. Okay, so maybe let me more cleanly. Okay, so how many poles and zeros do you think we have now? They have two capacitors. Can I set the initial conditions on the two capacitors independently without any contradiction? Why? Why or why not? If I set the voltage here, I can set this voltage here. What's the problem? This node is not coupled from this, right? There is no relation between these two nodes now actually. Oops, sorry. With respect to initializing the capacitor voltages, I can have two independent voltages set there. Is that fine? Only if they are coming in parallel or series, I cannot do it, right? Here they are two different nodes, I can do it without any problem. So how many poles do we have now? 2 poles. Do we have zeros or we don't have zeros? So this is the output, remember? We have 1 0, right? Because I can see if I short this capacitor, output is grounded, but I can basically short this guy and still get a non-zero output. Okay, and that should also not be okay. Let's do it. Is 1 0. So I am interested in writing the transfer function. So first let me write the DC gain. What is the DC gain? GM of n. GM of NMOS times R naught of NMOS is infinity. So just R naught of the PMOS. So I'll just say some R naught. That's all. Okay. So here is where I am applying the input. So this is now a simple common source structure, that's all. Just have one half of it to worry about. Great. So what is the first pole location? Let's say at this node. What is the pole location due to this? Huh? Yeah, so it's basically the R output resistance by this. I'll just say, oops, minus G naught by CL. What is the second pole we have due to this capacitor? The capacitance is C1. So what is the impedance we have looking in? 1 by Gm. Okay. You also have 1 by Gm parallel R0 of the PMOS, but for all practical reasons it's 1 by Gm. So what is the pole location? Minus Gm of the PMOS by C1. Okay. So the only thing pending is finding the 0. Now again, for 0 you see that you have at the output you have current coming in this direction, you also have current coming in this path, right? Oops, sorry, disappearing pen. So this path is 1 and you also have a current coming because of this, and the path which I have marked here sees a capacitance, so that has a different phase shift. So these two will add to give 0. So to find the 0 location, again I will do the same thing. I will assume output is 0. So which means if this is 0, no current flows here. So these two currents must add to 0, right? So if I mark this current, say I2 and I4, oops, say this is I2 and I4. So can you tell me what is I2? Gm delta V by 2. That is fine. Oops. So now let's first let's look at this current. What is this current I1? Minus Gm delta V by 2. So this current I1 is going to flow into this node and generate some voltage which I will call V3. What is V3? Let me write it here. What is V3? Tell me in terms of I1, right? So V3 is I1 times what? No, but you don't have just Gm, right? You also have something there. I mean, this current I1 flows into the effective impedance you have at this node. At this node, what is the impedance you have? Resistance you have is 1 by Gm. You also have a capacitance in parallel which is C. Okay. So you have I1 into basically 1 by Gm of the PMOS, 1 by SC. So I mean this basically I1 by GMP plus SC. Okay. So oops, I think everything disappeared. So this is V3. So this is also V3. So now what is this current I4? GMP into V3. Same thing. So if I do that, I will have GMP times I1, and I1 in turn is minus Gm delta V by 2. No, actually, okay, I4 is what? Can you check carefully and tell me? In terms of V3, what is I4? Can you check carefully? Gate voltage is V3. I am looking at the current in this direction. Huh? There will be minus sign. Okay. I mean, GM VGS is the current flowing from drain to source. So here I am considering the current from source to drain. So this is going to be minus GMP times V3. Okay, is that fine? So this is going to be what? Minus GMP times I1, and I1 in turn is minus GM times delta V by 2. So if I do that, I'll have everything is GM NMOS. Okay. So I mean to find the 0, I'll just do I2 plus I4 is 0. Okay. So let me make some space. So please work out and tell me what is the 0 then. We have all the information you have on the screen. This is I2 and this is I4. Sum of the two is 0. What is 0? 0.C1. Okay, I mean, see, this guy is common in the 2, right? So it just becomes 1 plus GMP by GMP plus SC1 to be 0, and you work out and the 0 will turn out to be this. Right, so now we have everything, so let me write it separately. So I have a pole at minus G0 by CL. I have one more pole at minus GMP by C1. I had a 0 at minus 2 GMP by C1. Okay, so usually this is also called the mirror pole, because it comes due to the current mirror we had, the PMOS current mirror, and these two guys together, they are called the pole 0 doublet. Because the same capacitance actually gives rise to both pole and the 0, and look at their locations, right? They are actually very close by. Okay. So now do you think P1 is greater than P2 or P2 is less than P1 is less than P2? Huh? So P1 is less than P2. Is that fine? Okay, P2 is a low frequency pole we have, because again GM is going to be much larger than G0, and at the output I also will have some load capacitance, so that's going to increase the denominator here. So P1 will be actually smaller than P2, and this low frequency pole is often called the dominant pole. Have you come across this term, dominant pole?
Yes.
Okay. Why is the low frequency pole called the dominant pole?
Because it will start falling, gain will start falling.
Not okay.
It will determine the frequency.
Huh?
It contributes more in the response.
Can you? Yeah. Can you elaborate more?
Near to the origin, so if we got it in pretty near to the origin, so stability will be more dependent on that point.
No, I mean, why is it dominant pole? I mean,
Because this, the other pole will be far away, so that will won't be contributing the stability.
no, but he mentioned about time domain response, right?
But again, let us assume that one pole is h goes to minus 1, another one is h goes to minus 100. So if we take in response in time domain, so it will come like e to the power minus 100 into t.
Exactly. Okay. So I mean, the point is, you have two poles P1 and P2. So basically, you will have something like this, right? S plus P1 times S plus P2. So if you take the time domain response, say impulse response you take, you will have basically something like this. Okay. So basically both are exponentials. So one might do this one might do this. So which is corresponding to P1 and which is corresponding to P2? If P1 is smaller than P2, white one is white is P1. Is that fine? This will be P1, right? Because this guy will decay quickly. So finally, in the step response or settling, you will see that P1 will dominate. Okay, so usually it's called the dominant pole. So if that is called the dominant pole, what do you think P2 called? If one is dominant, what should be the other called? Okay, you are going to name it. What will you name it? If I call one as dominant pole, what will I call the other one as? What? SSCD? What? SSCD, man, don't go to too much of English, man. Simple English. Opposite of dominant, man. If you are a second standard kid. Non-dominant pole, that's all. Okay. Any poles, any other poles you have in the system, they are called non-dominant poles. Okay. So, basically now if you try to plot the magnitude response.
Dominant pole also determines the cutoff frequency.
Yeah, that's what, there are multiple reasons, like we'll see now. So, you'll have the first dominant pole coming here, P1. So, it will drop like this. And then you have the second pole. So now it will go as, what is the slope here? Minus 20 dB per decade. Now you see the second pole, it will roll off as, okay, like this, minus 40 dB. And then you encounter the 0. Right, okay, assume that this is minus 40, and then it will again go as, okay. Great. So just have a few minutes. So what I wanted to probably quickly comment about is, let me take this guy. So this was a part of the assignment 1 question. I don't know if everyone solved it. So the question was, find the gain at this node, right? What is this? This was one of the questions. And here one interesting thing is, if you try to find what the output resistance here, right? Okay. So I'm finding the output resistance. I will short all the other one. So what do you guess the output resistance is? It's not really correct. The quick guess might be it's 1 by GM of the PMOS, but it turns out it is not quite true, because say you apply a test voltage here. This PMOS is going to draw current, which is GMP times V test. Okay, so the same gate voltage is applied to this PMOS also. What will be the current? This guy. So if you assume all the R naughts are infinity, so this current will actually has to come like this. Okay. So what is the total current we have here now? 2 times GMP VT. Okay, so what is the output impedance now? So R out looking into that node is actually 1 by 2 GMP. Okay. And again, if you actually include R naught, now what you will have to do is, this GMP VT current will have a path to flow into the R naught of the PMOS, and whatever impedance we have looking down. So we will have basically a current division between this impedance and the looking down impedance, and whatever current flows down is what will actually come. Okay. So again, you can take it as an exercise and work out in presence of R0N and R0P what R out is. Okay. And find out. Okay.
R0N will not affect.
It will affect. If this has an R0N,
But the current.
No, the point is the PMOS will have a current source VGS, GMP-VT. So that current can either flow into R0 of the PMOS or whatever the impedance you have looking down. So you'll have a current division between these two impedances, and whatever current flows into the impedance looking down is what will actually come up. Okay? Is that point clear? Okay, take it as an exercise and work out.